everyone, I'm Libby Hopfauf. I'm the Program Manager and Audiovisual Archivist for Moving Image Preservation of Puget Sound, or MIPoPS, and I'm also the Audiovisual Archivist for the Seattle Municipal Archives.
And I'm Dave Rice. I'm the co-chair of the EMEA Open Source Committee.
We would like to begin by acknowledging that MIPoPS is located on the ancestral homelands of the Coast Salish tribes, past and present, and honor with gratitude the waters and the land itself, along with the peoples and cultures that have existed here since time immemorial and continue thriving here today. This acknowledgement does not take the place of authentic relationships with Indigenous communities, but serves as a first step in honoring the land we are on. Welcome to our NWA 2022 project update for DVRescue. In this presentation, we will demonstrate the current development status of DVRescue tools, summarize project conclusions, and describe future work for digital videotape preservation. DV-tape refers to a family of digital videotape formats including mini-DV, HDV, DV-Cam, and DVC Pro, commonly used from 1995 through the 2010s. The affordability and compact size of DV-tape enabled many cultural, journalistic, and humanities organizations to create unique audiovisual documentation for the first time. These formats were not commonly used for media distribution. Thus, a collected DV tape is likely a camera original or a unique recording rather than a copy. DV tape is far more susceptible to contamination, damage, decay, and environmental factors than any other videotape format from the same time period. At the peak of its era, DV was well supported by multiple software applications such as Live Capture Plus, DVGrab, and Final Cut Pro 7. However, now nearly every application supporting the transfer of DV is unsupported. Websites are offline, aged applications are difficult to access, and such applications do not or cannot run natively on modern computers. Premiere Pro and QuickTime can both still transfer DV tapes, however, they do not capture the raw DV stream. Funded by a research and development grant from the National Endowment for the Humanities, DVRescue is a set of tools designed for preserving archival videotape in DV formats. Over the past 2 years, this project has developed procedures and tools that support migrating data from DV tapes into digital files suitable for long-term preservation. This has helped fill an urgent need for DV tape transfer tools that can rescue content from at-risk digital videotape formats. During this project, we have been and will continue working to develop open source and freely available software, user research and testing, and create documentation to help define and perform comprehensive, automated, and easy-to-use data migration techniques. As part of the collaborative effort, MIPoPS and RiceCapades selected and invited a group of participating institutions currently collecting DV videotape to allow us to conduct research, define preservation workflows, establish standards, and develop the most impactful tools for capturing content from DV videotape. Our participating institutions include the groups represented on this slide. At the beginning of the project, we took an initial survey of our participants. The gathered data aided the development process based on group-specific needs. In order to determine which groups could test components related to specific formats, we requested information regarding DV formats they had in their collections and which of these they were able to transfer in-house with decks they currently owned. To ensure that DVRescue would be compatible with the workflows of our test group, we also inquired what types of operating systems they were using, along with which capturing softwares. To ensure effective instructions for using the tools and provide a variety of resources, we wanted to make sure we accommodated all learning styles and skill levels. This is a MIPoPS standard, but we consistently poll users to ensure we are addressing their needs. The tools included in the DVRescue software are DV Guidance, DV Capture, DV Analysis, including DV Play filters and DV Loop functionality, DV Packager, and DV Merge. The current state of each of these tools will be demonstrated in this presentation. As I mentioned, one of the components of DVRescue was and continues to be developing and piloting universal training materials and tools for ready deployment using our partner institutions as a test group. As the tools enter their final stages, we're currently working to finalize materials and add them to the DV Guidance page in order to keep the images and instructions as up to date as possible. In order to provide accessible training and guidance to the archival community, our goal was and is to produce documentation that addresses all learning styles and skill levels. DV Guidance comprises a sort of encyclopedia for all facets of DV videotape preservation. The documentation is and will continue to become available in both on and offline formats. We're providing video, audio, textual, and visual examples and instructions to address the following topics: background and history of DV, DV formats guide, training videos and documentation, transfer station setup instructions, shopping lists, deck guides, file care, or post-capture best practices, capturing best practices, artifact identification and solutions, glossary, and additional resources. In order to empower organizations not currently digitizing in-house to set up DV workstations or to assist with the workflow improvement and maintenance for those who are, we've compiled resources to make the process simple, cheap, and easy. These are currently available online, and this is an example of the PDF offline format. While all of these sections will be updated as needed to accommodate changes and reflect improvements and modifications, some of them will be contribution-based living documents, such as this deck guide. This will be a fantastic collaboration opportunity similar to AV Artifact Atlas to have people add to this list with additional decks accompanied with their experiences and the specifics of each one. Currently online are our setup instructions and transfer recommendations for all operating systems, including Mac, Linux, and Windows. These instructions include specific details for all possible configurations, cords, and adapters needed for all deck outputs and available parts on multiple generations of computers.
The analysis section of our GUI is what shaped up first. This interface depicts a timeline of a DV file and shows the rate of video and audio errors over that timeline along with recording events such as start and stop markers and jumps in the timestamps or the timecode. This interface basically depicts the XML that we store behind the scenes that documents the transfer event or the evaluation of a DV file. This interface shows 3 ways of interacting with that DV data about the transfer. There's a player, a table with data about interesting frames, and a graph. The interface is designed to keep all 3 of these components in sync, so a highlight will follow along the graph or the table according to what frame is shown in the player. When the tape is read inside the deck, it's read by a drum with 2 readers, one on each side. Since the tape transfer errors can be sorted by which reader they came from, our graphs are centered, with errors coming from one reader plotted upwards and errors coming from the other reader plotted downwards. This helps clarify if the errors were because of an issue on the tape, where the errors would be distributed equally between both readers, or if the errors were because of a deck issue, where like one of the readers was clogged and produced something like a head clog. In the frame table, we also show information like the embedded timecode, the recording timestamp, and the properties of the file, like the properties of the frame, such as the aspect ratio and the audio channel characteristics. I mentioned earlier that the processes we're designing to capture DV from a tape to a file, so I want to give an update on that work. Currently, the design of the capture process is in 2 pieces. The first is a receiver, and the second is a processor. The receiver varies a bit depending on what operating system we're supporting, so FFmpeg is used to read from a DV deck to a computer on Windows and Linux, or we have our own tools based off AV Foundation in Mac operating system. The second component I mentioned in the capture workflow is this processor, and that is in our DVRescue command line tool. The role of the processor is to receive the frames, analyze them, and resulting from that analysis, take some type of action. Normally, that would be writing it to a file, but it could also be adjusting how the frames are received or controlling the deck. So one tool I mentioned in our spring EMEA presentation was a method to allow that processor to receive multiple copies of the same DV transfer so that it could merge them together in a process to create one better output. It could do this by relating all the frames of each copy, finding where the errors were, and replacing erroneous data in one copy with any better component of the additional copies for the same frame in the same position. DV tapes are finicky, so from one reading to another, they may have the same rate of errors, but the errors might be in different places. In this image from our earlier presentation, I'm showing 6 transfers of the same tape where my friend Ben's face has some errors over it in each one. Those frames are then combined in the merge process to make like one better output. So lately we've been combining the capture process and the merge process together to test workflows where we capture a tape, rewind it, capture the same tape a second time, and then merge those 2 copies together to make a better result. But it takes about double the time. So the new process we're experimenting with is having the processor identify the errors and selectively retry portions of the tape while capturing. First, the software begins capturing DV frames and looking for errors as it does. When an error is encountered, such as an audio dropout or video error concealment, Then the processor begins to look for the next frame that does not have an error. When it gets to a good frame, then it stops and it rewinds to the place before the error started. And then it starts reading from the tape again until it gets to where the error ended. Then it rewinds one more time and reads from there and then keeps going until the next errors. So in computer memory then, we're managing 3 different readings of an errored section and combining the best parts of each to make one better output. Having this triple take on sections with known errors gives us a more accurate output than is possible in a single take. And in this clip, you can see the triple take in action on this deck, which is showing a preview of the image and the timecode. So you can see as it's playing along, the software notices the error and begins a process of rewinding to do this kind of triple take pattern, where a section of the tape is reread multiple times as the continuous capture process continues. We're still experimenting with this and might add a step in where we try to read the frames during the rewind step 2 to gain the most opportunities to read from an errored section of tape with the least amount of wear. As we're wrapping this up, we hope to merge this into the GUI soon. We're still kind of working on what we need to do to set up the GUI so that the player can play frames that are held in memory, so the user can see what the deck is doing as it's capturing. But this is one of the parts of the project we're most excited about, where we have the computer kind of selectively controlling and intervening with the deck to make the best output it can. Part of our approach for capturing DV data from a tape to a file is to receive each frame, frame by frame, and write it continuously to a single file, even if the characteristics of these frames change. For instance, we may capture a DV tape even though the audio changes from 48 kHz to 32 kHz per second. Or it could change from 4 channels of audio to 2 channels of audio and back. Or the aspect ratio could change between 4:3 and 16:9. Capturing tapes as continuous data streams, regardless of changing characteristics, helps us avoid the old issue of a capture stopping at every change or timecode break, like Final Cut 7 or Premiere used to do. And this makes it easier to transfer all of the data from a DV tape into a file in its entirety, despite those potential changes. However, this creates an interoperability and playback issue, as many players don't well support variable aspect ratio or variable sample rate. So in the DVRescue project, our focus on packaging is working to address the issues of storing an unprocessed data stream known as a .dv file. We use the term packaging to mean encapsulating that DV data stream into a container format such as QuickTime or Matroska. In a format like this, the characteristics of potentially broken or inconsistent DV files read from a tape may be expressed with more clarity. Moving a DV data stream into a container also lets us use features of that container to make the content more convenient and accessible. For instance, in addition to the video and audio, a DV stream might contain timeline markers, captioning metadata, camera metadata, and metadata about how successfully that data was transferred from the deck. Much of this data is very difficult to access in available software. So the packaging process we're using is intended to interpret or move that data to things like chapter tracks, subtitle tracks, and embedded metadata within the container, which is much more accessible and usable in players like QuickTime X, MPV, or VLC. When packaging DV into a container, the DV data is copied as is into the QuickTime or Matroska file, and it just becomes the video track as it is, with the audio, captions, subtitles being kind of encapsulated along with it. In most cases, one DV tape will be captured to one DV data stream file and then packaged into one packaged file, one QuickTime or Matroska file. That is, one tape to one data stream to one container. But in some cases, the changing characteristics of a DV recording might make this difficult. If we had a DV file change from 4:3 to 16:9 aspect ratio, the packaging process might decide to split that up and make one contained file for the 4:3 part and one for the 16:9 part. Beyond segmenting files according to their technical characteristics, we also support options to segment files during packaging according to other recording events as well, like recording start markers, timecode jumps. So I've presented on the script or the process we have called DV Packager before, but I'd like to give a bit of an update to our work. After our last presentation, we changed the default packaging output format from Matroska to QuickTime, as we found most of our users that were testing our work were using QuickTime rather than Matroska, and it also seemed that nearly any environment that could play DV could also play QuickTime, whereas this was a bit less true for Matroska. We also cleaned up the chapter titles so that now chapters in a file are named after the source timecode and the camera recording timestamp. We've also added a method to determine if the output file should have stereo channels of audio or mono channels. While most DV tape is intended to have stereo paired audio channels with a left and a right, sometimes DV is recorded differently and we'll have a different recording on each channel. Because DV just has 4 channels of audio, it doesn't necessarily express any clarity as far as how they are supposed to be arranged. We also put more attention into DV Packager's handling of damaged section of DV, particularly in relation to audio. Often when DV tape is damaged, the audio won't be read properly, and then you can have a DV file where there are portions of the data stream that have video, but they don't have any audio. This has been a little tricky to manage because some container formats like QuickTime don't have a good method to store gaps in a audio track where there's just no audio at all, not silence, just no data. So in the DV Packager process, we have to identify where those gaps are, and the packaging process fills it with silence instead of an absence of audio in order to keep the output results synchronized and continuous. Because before we were finding problems where like FFmpeg would be sending out video, sending out audio, but all of a sudden you'd have these frames of video and no audio. And then when the audio came back, it would just kind of be offset and there'd be like a gap or a synchronization issue from that point on. So by covering those gaps with silent audio, we're able to kind of manage everything and keep it in sync on a continuous timeline. We're also still finalizing work on DV Packagers. So we've been adding a lot of verification and testing into it so that we can make sure the output is as expected. So we track packaging errors that can happen with very damaged or very unexpected DV data streams. The main kind of errors that we've been finding is when the output file is missing altogether because DV Packager is constructing a command to FFmpeg that it isn't able to actually process to make the output file. Or we find files that sometimes have a different duration for the audio and video track where they're intended to be the same. Another kind of error is that sometimes the output file doesn't contain the same number of frames as the input file. So in these 3 cases, like we're doing all the post-testing after the packaging process to make sure everything worked appropriately and to note when it didn't. As we've been working more and more on DV Packager and with exceptional files from like our testing users, we've been able to like substantially reduce the amount of problems that come up in the packaging process. But we still have all these like little verification steps in place to identify when they do. Because our goal is to have packaged, clarified, and interoperable QuickTime or Matroska files that are also able to recreate the original DV data stream if needed. So that's the update on DV Packager. This exists as a command line script that can be run with all the options, and has also been recently integrated into the graphical user interface that we're developing so that you can take .dv files and package them into containers with the segmentation options you prefer. Thanks.
The work completed for DVRescue has unearthed a broader need in the archival community to expand current analog workflows to address the unique characteristics and issues that impact a variety of additional digital videotape formats. Thanks to renewed financial support from NEH, our new project, Digital Video Commander, will build on our findings during the early stages of DVRescue. This expansion project will entail 2 additional years of work to develop open source and freely available software, user research and testing, and create documentation to help define and perform of comprehensive, automated, and easy-to-use data migration techniques. We will continue working with 9 partner institutions currently collecting digital videotape to conduct research, define preservation workflows, establish standards, and develop the most impactful tools for capturing content from these additional digital videotape formats, as well as enhance the tools created as part of DVRescue. Digital videotape deserves and requires a fundamentally different approach. Whereas calibration of the signals from a played analog videotape are essential prior to digitization to ensure that the resulting digital file represents the full quality and potential of the recording, such manipulation is detrimental to playing back digital videotape since it is already digital. Adjusting the brightness, color, or volume of a digital videotape may still be helpful. However, such adjustments could be more easily applied to a resulting digital file, whereas not calibrating an analog videotape could result in irrevocable loss. Our research within the DVRescue project has proven opportunities to preserve DV tapes more reliable by developing software that works with the videotape player to gather the more accurate and complete representation of the DV tape's contents. By applying a similar process as sector-based disk migration, we believe we'll be able to capture a more complete file from other digital videotapes. As indicated by the name, the process operates by copying the source file sector by sector, rescanning as it encounters an error. Rather than simply recording a file of what a video player is presenting, the recording software coordinates the entire process by assessing the data continuously, controlling the player to make second attempts as needed, or guiding the user through easy-to-follow corrective actions. The Digital Video Commander project extends these findings from DV to all digital videotape formats.
As Libby noted, one of the central discoveries of the DVRescue project has become a stepping stone for the new Digital Video Commander project that we're just beginning work on. We found that we can improve the migration of DV data from DV tape by selectively rereading parts of the tape of errors more than once and combining the results according to the embedded error status information. So we'll be working to extend this approach to formats such as digital Betacam, Betacam SX, and HDCam. This project has shown us a new concept of transferring data from videotape. The traditional approach involves an assembly line of processes where the videotape plays a signal that the computer receives and records. In this new approach, the computer software orchestrates the capture event, commanding the video deck to play, receive, and evaluate the content, and request the deck to rewind and retry if errors are found, and orchestrates like receiving frames and deck control, evaluation, to come up with the best output possible. So rather than the computer diligently writing all the data it receives, the software is more active and controls the deck as needed, potentially in multiple passes, in order to make the transfers more accurate than would be possible in a single pass. With this approach, the software could even stop writing the data and ask the user to clean the deck if head clogging issues are detected, and then synchronize the tape back to where it left off and continue. With DV, the error codes are clearly embedded within the DV stream that's transferred over FireWire, and each frame is identified with those time codes and absolute track numbers. With formats such as digital Betacam and Betacam SX, which would be transferred over SDI, there are new challenges in doing the work to identify the tape transfer errors and determining the identity of every frame so that we could match frames across multiple passes. And then we also need to create a new, open, reproducible, and accessible way to do deck control. So that's one of the earliest challenges in this project that we started to address. So I'd like to go into that in a bit more detail. So in the DVRescue project, we used a variety of tools such as DVCont and our own development to send control codes over FireWire to the deck to do two things. The first would be to control the deck, such as making it take action, such as stop, play, rewind, and fast forward. The second thing that this interaction does is query the deck, asking it for information like the model name, the time code of the current frame, and the settings of the deck. So we have this kind of interaction resolved with DV in the DVRescue project, but we need to do this with digital Betacam decks, Betacam SX decks, and others. So in order to use a computer to control a deck, often we're using a video capture card. So for instance, the Blackmagic Ultra Studio offers a remote output, so you can connect the Ultra Studio Express to the deck with a 9-pin cable, and then you can control the deck from your computer using Blackmagic software or tools that are integrating Blackmagic software development kit. But many modern capture cards don't have this remote option. And we're interested in reducing the dependency on specific pieces of proprietary hardware to perform deck control and to create a more affordable, approachable solution, potentially independent from video capture. So we worked with a developer who had created a set of code for performing deck control with an Arduino at this GitHub repository. So we approached Heidecke to see about extending the work here to remove the Arduino dependency. Because we wanted to get to the smallest set of hardware possible to have a computer and a deck interact together. So eventually, through collaboration, sponsored development, lots of testing, and building upon other open source building blocks, we eventually developed a command line program that was able to do deck control with a specific set of hardware. This is what our prototype cable looked like. This uses a USB to RS422 adapter, a DE 9-pin breakout board, and then jumper cables that I borrowed from my son's Raspberry Pi kit to connect the two devices together with a custom mapping that would work with the Sony 9-pin protocol. The other thing I wanted to show off here is beyond just controlling the deck, we also want to query it for information. So in our query results right now, this is how we're detecting the information that comes back from the deck. So it tells us information about if the deck is in local or remote mode, if the tape is in there, what the mode is of the tape, like if it's actively playing or fast forwarding. We're able to ask for various types of time code. So we're really excited to get this kind of raw information back from the deck and determine how we're going to use that and capture it before or during a transfer.
An initial task for the Digital Video Commander project involved building customized cables. So far, we have successfully established best practices and instructions for 2 versions of the cable. These cables enable remote deck control, as we have established with DVRescue for controlling DV decks. Using the 9-pin remote port on the back of any deck, these cables allow not only digital videotape decks to communicate remotely with the Sony 9-pin command line tools, but enable basic operating functions to be executed for any connected deck, such as play, fast forward, rewind, stop, pause, and eject. Version 1 of the Digital Video Commander cable is less time-consuming and requires fewer supplies to build, but it is a little messy and the wires can come loose more easily during transport. This is easily resolved, but it is a factor to consider. Version 2 requires additional supplies, time, and a basic understanding of wiring, but the result is a more durable and sleek design similar to the other various AV cables we are used to. Both of these cables are relatively inexpensive and straightforward to assemble. For both, we have developed documentation that includes a list of supplies, a wiring map, and step-by-step assembly instructions. Later in this project, we'll be creating demonstration videos for cable building, deck cleaning, as well as how to use the tool sets for DVRescue and Digital Video Commander. Instructions for building these cables can be found on the Digital Video Commander documentation website, along with instructions for setting up connections between decks and computers for all operating systems and draft documentation for testing your cable using the Sony 9-pin command line tool. To learn more about DVRescue and Digital Video Commander, you can check out related resources online. From the main MIPoPS page, you can access our blog, code base, and all the latest documentation. For feedback, we highly encourage you to create an issue in our GitHub Issues tracker. The tracker provides a transparent, community-based approach to meeting the needs of all users. Others can weigh in to brainstorm or concur, allowing us to prioritize development and ensure documentation is effective. This should also be your first stop when performing your own troubleshooting for DVRescue tools. If you're experiencing a problem, chances are someone else is as well, so you can see if any of the issues posted sound similar to the one you are encountering, and if there are any steps you can take to solve it. From the main DVRescue GitHub page, you can find the link to our daily builds. It's in the far right corner under About. Here you can download the latest version and keep track of our progress as we address development work, improve the GUI, help fix the bugs, and add the features that you ask for in the issues tracker. If you're uncomfortable using GitHub, just email us. We also have a documentation page where you can access additional resources. We'll be adding to this as documentation is finalized and new discoveries are made. This project is intending to provide context to not just how DVRescue, the software application, works, but as a holistic approach to comprehensively managing your DV collections, with everything from initial assessment to understanding format specifics, to how to set up a transfer station, to how to prepare tapes for capture. We aim to provide all the tools you need to manage and care for these physical objects. Right now, there are 2 locations that you can go to find information about the DVRescue workflow: the DV Guidance website and a MIPoPS Google folder for doc development. Both of these are available from the main GitHub page. I would like to note that the state of this web documentation would not have been possible without Ashley Bluer, who did all of the initial prototyping and design for both the documentation site and the GUI. Digital Video Commander has its own GitHub page. Since development on the project has only begun, resources are limited, but Andrew Weaver is quick to post new documentation as we create it. Beyond capture, these resources provide guidance for file care, identifying artifacts, and possible resolutions, as well as additional resources to help you digitally preserve the important content from DV and other digital videotape formats in your archive. Since you can't click on this video, it will be posted to YouTube, and all of the links listed in this presentation will be included in the description.